Hello everyone, this is Athota Rathan Babu, working as an assistant professor in the Department of Aeronautical Engineering, and I'm dealing with the course Computational Aerodynamics. And in today's topic, we will see the basic problematic cases and case studies on the module 3, which is basic discretization method. So in that, we will see especially how do we solve numerically the diffusion equation. So basically, we have seen the approaches of finite difference method, and we have seen the approach of finite volume method. So in the finite difference method, so we have explicit method and we have implicit method. Now in today's session, we will see how do we code it, like basically how do we solve it numerically using some coding techniques. So that we will see in detail. For that case, like we have taken a diffusion equation. So in the previous session, we have solved so the diffusion equation and Laplace equation and the second order wave equation explicitly and implicitly. Now, so we will see that and we will code it in any numerical techniques. So like you can take MATLAB or Java or any kind of programming language. So here solve the diffusion equation with a numerical technique. So numerical technique. So basically, I will use finite difference method. So for the finite difference method, we have explicit and implicit. So we will see that explicit and implicit programming nature actually. So we will actually solve this one with explicit and implicit. So we'll solve this one with explicit and implicit. So first, let us write down. So what is the diffusion equation? So there are two kinds. So basically, 1D diffusion equation, 2D diffusion equation, 3D diffusion equation. So you can take 1D unsteady diffusion equation, or you can take 2D unsteady diffusion equation, or we can take 3D diffusion. So let us write down what is diffusion term. Dou square u by dou x square. So this is basically simply 1D diffusion. So we don't have any unsteady term here. Okay. So when we include a time derivative term to this expression, so it becomes, so let's say dou u by dou t plus dou square u by dou x square is equal to, let's say, 0, or you can take this. So minus c is equal to 0. So this is a 1D which will have plus unsteady term. Okay, so we will have unsteady term. Now what we have, so this is 1D. For 2D, what we will have, so dou u by dou t plus minus c into, so dou square u by dou x square plus dou square u by dou y square. So this is what we have. Next for 3D, so this is for 2D. So for 3D, what we have, so dou u by dou t is equal to c into dou square u by dou x square plus dou square u by dou y square plus dou square u by dou z square. Okay, so this is for 3D. So for these three aspects, so let's say we will see the explicit method, and already we have discussed, but we will see in detail the explicit and implicit method and the numerical procedure in any one programming language. So you take object-oriented programming language, or you take simple programming language is MATLAB. So where we will discuss in detail about these aspects. Okay. So first let's write down. So this one in explicit approach. So when we write down this one in explicit approach, so let us write down for 1D. So 1D unsteady diffusion equation. So what happens? Du by dt minus c dou square u by dou x square is equal to 0. So this is what we have. So here what we will do is like we will write in terms of first in discretization method, and which is in explicit form. Then we will write down the code. okay, generalized code. So you can apply it for any programming language, as I told you. So you can use for C++, MATLAB, or Java, or any kind of programming language you take. So you can do it. But here I'll just give the generalized concept, like how like we will actually write down in a code terminology. Okay, so like how do we give the boundary conditions, how do we give the initial conditions? So these aspects are very important. Okay, so how do we give these things, we will see. Fine. Now, so what do we do is like, so we will write down this. So we have u of I. So basically, since it is 1D, so it is u of I to the power of n plus 1 minus u of I to the power of n divided by delta t minus c into, so we have u of I plus 1 to the power of n minus 2 u of I to the power of n plus u of I minus 1 to the power of n divided by delta x square equal to 0. So this is what we have. Now what we will do is like, we will write down clearly. So unknown terms one side and known terms other side. Okay, so what happens, u of I to the power of n plus 1 is equal to, so u of I to the power of n minus c into delta t divided by delta x square into u of I plus 1 to the power of n minus 2 u of I to the power of n plus u of I minus 1 to the power of n we have. So this is the formulation which we need to write in any one programming language. So how many variables we have, like we have this, like we will write down clearly. So in the next page itself, so we will write down the equation, we will declare the how many variables we have. So u of I to the power of n plus 1 is equal to, so u of I to the power of n, next plus c into delta t, sorry, this would be minus plus c into delta t divided by delta x square into, so u of I plus 1 to the power of n minus u of 2 u of I to the power of n plus I minus 1 to the power of n. Okay, so this is the formula which we have. Fine. So this formula we need to write code. Okay, so you take any programming language. Let's say, let us compare between the MATLAB and the object oriented programming language. So let us take MATLAB and let us take object oriented programming. Let us take Java, actually any Java, or let's say derived programming, like object oriented programming language is C++, or you can take any of these. So we'll just compare, and we will like how to write this equation and solve this equation numerically, we will see. So first let us see for MATLAB actually how we can solve this equation using the MATLAB code. Okay, how do we write it? So first, how many variables we have, that we need to identify. So we have 1, 2 variables, next 3, 4, and c is constant, so we can take this one as constant. So delta t, let us take it as a constant time step, and delta x also, it is constant actually, so it does not vary with respect to simulation, and delta t also will not vary with respect to simulation. So that is what assumptions we will take. Now what is happening, so u of I to the power of n plus 1. So when we write the program, so first whatever the variables we have, u of I to the power of n plus 1, u of I to the power of n, and u of I plus 1 to the power of n, and next u of I minus 1 to the power of n. So these things actually we need to so we need to write down in any one program language terminology, or let's say we need to declare it. We need to declare it, so in such a way that we will actually, so we will have to calculate these aspects in sufficient mode. Okay, fine. So what happens actually? So let us take. So let us take in MATLAB. What we take is like we will declare variables. So let us take first the value of delta t. So when you start the programming of MATLAB, so what we will do is like CLC. So we'll keep clear all. Okay, so the CLC clear all this commands. What we use is like whatever unwanted garbage that comes in the command window or any other workspace. So it will clear off. So before running programming language. Okay. Now, so we will take the C, which is constant. C is equal to some value 1. So we can give dollar symbol and name it. So it is a constant for diffusion. So we can take in this way. So C is equal to 1 and which is constant of a diffusion. So this we can write. Next, so while writing any numerical solving technique, like you can take MATLAB, Java, or anything, so you should actually write down so the comments for the each variable. So let's say I have 4 variables, 5 variables, you can remember it. There is no problem. But when you let's say today you are writing this program, and after 1 month if you open like or 1 2 months if you open, you cannot recall it, let's say. So if you are writing c is equal to 1, let's say, or delta t is equal to some value, so these things you cannot recall. So that's why the best practice for any programming language is, so you need to give the comment such that you can recall what is that variable or what is that term called. So that's why, so for each and every term which we write here, so we'll give a comment like this percentile symbol for giving a name. Okay, so next we'll take delta t, which is equal to 0.05 seconds. Okay, so this one we will take it as time step. Okay, so this is the time step delta t. Next we have delta x. So delta x, let us take it as 0.05. So let us take this as spacing between grid points. Okay, so what do you mean by spacing between grid points? So you take like since we are dealing with 1D, so we will take only x direction. Okay, so y direction we are not considering. So you take a grid point here, you take a grid point here, or you take a grid point here. So the distance between these two grid points, so this will come as delta x. So this also will come as delta x. Okay, so let's just take this is 1 2 3. So this is delta x1, this is delta x2. If delta x1 is equal to delta x2, so what we say is that the spacing, so we have, it is called uniform spacing. Okay, so the spacing between two grid points, between 1 and 2 and 2 and 3, so we say that the spacing is uniform. So in this the assumption is, so we can write down here, the assumption is delta x1, so assumption delta x1 is equal to delta x2 is equal to delta x3, so on. So how many number of grid points are delta xn. So therefore this is coming under uniform mesh category. Okay, so we have declared C delta t by delta x square terminology. Now, so what we will do? So for u of I to the power of n plus 1. Okay, so that we need to write actually. So let us take this as, so let us give these values. Okay, so this one as u1. So this is as let's say this is u2. Okay, let us take I is equal to 1. Okay, or so in MATLAB it will start from 1. So let us take I is equal to 2. Okay, and n is equal to 1. So that is what we have. So what happens actually? U1 to the power of 2. This one will be U1 to the power of 1. This one will be U2 to the power of 1. And this will be, sorry, I is equal to 2 we are told. So this will be 3. And this will be U1 to the power of 1. Okay. So this is what we have. So let us write down here also. So for the sake of clarity, so that we can see in this programming language. So we have terms. So what? So U of I to the power of n plus 1, which is equal to U of I to the power of n plus C delta t by delta x square. So C we have given, delta t we give the value, delta x square we give the value. Okay. Next, what do we have? So U of I plus 1 to the power of n minus 2 U of I to the power of n plus U of I minus 1 to the power of n. So this is what we have. So first let us declare what is this. So what we have taken, so we assume that the I value is equal to 2. We assumed I value is equal to 2, and we have assumed the n value is initially, you can take it as 1. Okay, so I value is equal to 2, n value is equal to 1. So what happens actually? So U of, so what is I? 2. Okay, so U2 of n plus 1. So basically, so here we will take it as U2. Okay, so this is what we have. Next, for this, so how do we write the coding terminologies? So basically, U of 2 of t plus 1. Okay, we will take t as time, initial time, which is as 1 second. Okay, so t plus 1. Fine. So already, so for the sake of clarity, we will write in this way. So U of let's say U of 2 of t plus 1 is equal to U of 2 of t plus, already we give a value of c and this thing, c into delta t divided by delta x square. So these values were given into, so U of 3 of t minus 2 of U2 of t plus U1 of t. Okay. So this thing actually we will write in the programming language. Okay. So let's say what is happening actually. So here the value, so the time, as the time changes, so as the value of time changes, so how does this formulation change? We will see actually. Okay, at a particular grid point. Fine. So at a particular grid point, so let's say we are solving at a particular grid point 2. So this is what U2 is our concern. So at this U2, so at different time levels, so at different time steps, so what happens actually? So how do we solve this equation? We will see. Okay. So how many variables we have? We have U1, we have U2, we have U3. Okay, and we have U2 t plus 1. So if you see the equation, so U2 of t, this value is known parameter. U3 of t, this value is known parameter. So U2, this value is known parameter. So U1, this value is known parameter. Okay, so here let's say you want to run the simulation for 10 seconds. Okay, and delta t value, you know it actually, and you can do in this way, or you can do in another way also. So here we are calculating for only one grid point. So the other way of doing is, so we will write the finite difference formulation. So u of sorry u2 u of n plus 1 minus u of n divided by delta t. Okay, so this is what we have. So this is I, or this is I. Basically you can take u1 is equal to, so what do we have, c divided by delta x square, which is u of this, since these are the initial values, what we will do is like u of I plus 1, so to the power of n, minus 2u of I to the power of n plus u of I minus 1 to the power of n. Okay, since the what we will do is like we will take normal Euler differential equation. So this in turn, what happens, so basically we will take this one as u value. So u value, so of at the location I. So basically we are interested at the location I, or you can take it as u2. Okay, so u of n plus 1 to the power of I is equal to u of I to the power of n, next, plus c delta t by delta x square we have. So what we do, so we will write the same equation here, u of I plus 1 to the power of n minus 2. So here we are multiplying with delta t. Okay, so for the Euler difference, so what happens, so the delta t changes. So what we do is like we will iterate. So there are two things which I told. So where the simulation time changes, and so basically simulation time changes and the value of the grid points will change. Okay, so what is happening, so basically you can take it as u of f, like you can take this as u of f is equal to u1 of t, or you can take initial time, and this one is u2. Okay, and this one is u1, and this one is u0, which is initial value, or you can take same I value as 2. There is no problem. Okay, so let us consider I value as 2, again n value as 1. So what is happening, so what we are taking is like u of I updated value, so which is 2. ui of 2 is equal to u2 initially. So basically this is u2 which is of initial. You can take n is equal to 1 plus c delta t, what we have taken 0.05 divided by, so c also we have taken it as 1 divided by 0.005 square. So here what do we have, so I plus 1. So since these values are initial values, so we know, so what happens, u of let's say it becomes 3 minus 2 u of 2 plus u1. So what is happening, so these values are the initial values. So basically here for the right hand side, so I will not write about time, so that is why so you can see, so this is the updated value. Okay, so let me take, so u of updated at location. So what we have 2. So at a time interval when it is changing, so u2 value, how does it change? So you can write here or here, here, anywhere. So what we are doing, so here this index terminology, so this I terminology, so we can use and we can write elu. So where the grid point, so location changes from I is equal to 1, 2, 3, 4, 5, 6, 7, so on. Let's say in the problem, so we have 10 grid points. Okay, so this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So you have 10 grid points. For these 10 grid points, I just see, if you take this, this is the boundary point and this is the boundary point. So from here you will have the boundary conditions. Okay, so we will start solving from this point actually. So what happens? So when you are solving at this point, it is influenced by point 3 and 1. So when you're trying to, so this point and this point, so that is what I'm saying, the dependency of these two terms will come for this. Similarly, when you want to solve at this location, the influence of 4 and 2 will come. Okay, similarly when you want to solve at 4, so the influence of 3 and 5 will come. Okay, so this is what happens. So when you want to solve a problem at particular grid point, so influence of neighboring points will play a major role to calculate that value at the next time step or the next level. Okay, so that is what we have. So what we do is like, so u of I plus 1. Okay, so u of I plus 1, sorry, u of, let's say, or let's say u of I of n plus 1. So where t value changes. Okay, that's that value, that's what we have. Or you can take the I value changes. So anything you can, let us take the I value changes. So we have u of I, which is updating one. Okay, so at n plus 1 is equal to, so what do we do? So we will put a loop actually. So we will write in programming terminology itself. So what we do, let us take for I equal to 1. Okay, I less than or equal to 10, you can take I plus plus. Okay, so this is what we have. Okay, so here for the MATLAB, you can you'll keep it as end here. When you compare this one with the object-oriented programming, so you will write the open braces and the closed braces. So this is for the MATLAB terminology, and this is for the object-oriented terminology. Same, you will write for I is equal to 1, I less than or equal to 10, I plus plus. Okay, so here we'll just open the braces and close the braces. Okay, so here what we do is like the value of, let's say, u of final uf. Okay, at that location, so at t, so let's say here the t value, so let's is changing. Okay, so t value is at the next level, so n plus 1. So where we have taken n, we will take it as n plus 1 is equal to, so these other values which are present in the right hand side, so we have as what the updated values. So the u2 value at different locations, or let's say at different time values, we can calculate. Fine. So instead of this, you can take it as I. Okay. is equal to, so u, what is the value? We are taking it as 1. So u1 of 1, so which is initial, or you can take it as directly n. So this value is initial value which is known. Let us take it as u of I plus. So what we are doing, like we are embedding the formula, okay, and then c into delta t by delta x square. So here we have already given the values. So c value is given, delta t value is given, delta x value is given, t value we are starting. So instead of n, you can take it as t also. Next, plus, so here we will multiply. So we'll have u of I plus 1 minus 2u of I plus u of I minus 1. So here what happens? So the I value will start from, so basically 1. This is what the final one. Okay. So this is what u of I, which is 1, and c delta t. So before starting the simulation, what we require is, so the value of, we require what is the value of u1. So what is the value of u2? So what is the value of u0? For let us take u0. In MATLAB it does not support u0, but you can replace it with other terminology. But whereas in object-oriented programming language, so it supports. So the indexing starts from 0 itself. So in the MATLAB, so what do we have is like the indexing will start. I value will start from 1, 2, 3, so on till n what you take. But here for the object-oriented programming, so I value will start from 0, comma 1, comma 2, comma so on actually. Okay, so when we want to write this terminology in the programming, in the case of the programming language for let's say, what happens in case of MATLAB, so you should not have this u0, but why? Because index cannot be, it will give an error such a way that you cannot store u0, that error will get actually. Whereas in the object-oriented programming, so we will not get that error. Fine. So here what is happening? So we are actually solving this value I is equal to 1. So the problem here you can see is as when I is equal to 1 comes, so you will have u of 0. This thing is acceptable for object-oriented programming language, but this is not acceptable for MATLAB. So what we have to do? So initially we have to calculate this formulation, okay, for at the location I, or let's say you have to replace this one, or let's say you have to start the index I from 2. Okay, so that is what we have. So here you can start index from I is equal to 1, or let's say you can start from I is equal to 0 also you can take. But if you take I is equal to 0, this becomes minus 1. So that's why we have taken I is equal to 1. Okay, so I think you have observed the difference. So when we are comparing between the MATLAB and the object-oriented programming language, so what is happening? We for loop, so for MATLAB we cannot start from I is equal to 0. So I is equal to 0 is not possible, and I is equal to 1 is not possible. Why? Why? Because so here in the other terms it is okay. Like when you take I is equal to 1, so this will be uf of 1, and this will be u1, and this will be u2, and this will be u1. But here what happens? The last term will have u0. So as I told you, the MATLAB will not accept that a memory allocation of u of 0. It will give error. Similarly, first when you are taking when you are not able to take I is equal to 1, you cannot take I is equal to 0 also. Okay, so it will give an error like index bounced. Okay, so that's what you get. Fine. So when you take, let's say I is equal to 0, here it becomes u of minus 1. So u of minus 1 is not at all possible actually. Fine. So therefore what happens? You will go with I is equal to 2. So here in this case what happens? So the how the loop continues. So you will take I is equal to 2 initially. So this will be u2 and this will be u2 and this will be u3. So we'll see this will be initially when I is equal to, so this will be uf of 2. So this will be u2. Okay. So this will be u2. This will be 2 of, so this will be u3. 2 of u2 plus this will be u1. So now this uf of 2 has to be calculated actually. So at the next time level, what is happening? Fine. So what is happening? So we are running for all the grid points. Okay. So please note that. So we are running for all the grid points. So that's why we are taking I is equal to some 2. So at this point it is not possible. And in the programming point of view also, we have seen that I, let's say you cannot take 0. So in the realistic scenario also, there is no point called 0 here. Okay. So that's why it was not possible for us to take. So what happens actually here? So the I value so is starting from 2 and it is ending till 10. So I value will start from 2, next 3, next 4, 5, 6, 7, 8, 9, 10. So when it is satisfying this condition, then the loop stops. Okay. So what is happening actually? So these values, so matrix laboratory actually. So it will store the values in terms of matrix actually. Okay. So you can, if you want to see the value of uf, so at 2 you can open the list of uf. So uf of 2 you can do it. Okay. So where uf of 2, if you type, so it will give you value in the command window, or you take uf of 3 in the command window, it will give you that value. So what is happening initially, we will calculate at one time level. So that input will be given for this. Then so u2 is already known for the initial value. u3 is already known with the initial value. So u1 and u is already known with the initial value. So we will supply here, and when we are calculating, so we are calculating at the next time level. Okay, only next time level at different locations. So first we are solving at 2. So we got next I value changes at 3. So what happens? So we will write down here again. So u of let's say I, uf of I is equal to u of I plus c delta t by delta x square into u of I plus 1 u of I plus 1 minus 2 u of I plus u of I minus 1. So I is equal to 2 we have seen. Let's say I is equal to 3. So uf of 3 is equal to uf of 3 plus c delta t. So let's give value here. 1 into 0.05 divided by 0.005 into, so this will be what we have taken I value 3. So this will be u4 minus 2 of u 2 of u3 plus u2. So this is what we have. Now, so uf of 3 in the sense, so the meaning is updated value or the next value or the value at the next time step at the grid point 3. Okay, so we have taken this. So initially, so we have like before starting the numerical problem, we will give boundary conditions. So boundary conditions is what is the value of velocity here on the boundary, here on the boundary you can say. Then we will give the initial conditions. So initial conditions, in the sense, what is the value of velocity at grid point 1 initially. Initially, in the sense, at n is equal to 1. At n is equal to 1, so what is the value of velocity at grid point 1? At n is equal to 1, what is the value of at grid point 2? At n is equal to 1, what is the value at the grid point 3? At n is equal to 1, what is the value of the grid point at 4? At n is equal to 1, what is the value of grid point at 5? At n is equal to 1 at 6, 7, 8, 9. So initially at time t is equal to 1 second, or let's say initial things, so we will assign the values. Okay, after assigning the values, what happens actually, we will substitute in this formulation. So we are calculating the updated value of the u2. So boundary value will not change actually until unless we does not constrain on the boundary. So this value does not change. Okay, so if we are giving a constraint that value at point 1 should be always so zero velocity, let's say that is no slip wall, or you can take slip wall. So if you have the no slip wall condition, you will take it as 0. So at 1 and 10, so you have a condition that the velocity is 0. So other points you will have the velocities. So what happens actually, so the value of 1 and 10 for all the time steps, so it is 0 only. Okay, so therefore what is happening, u2 of f, what is the meaning of u2 of f? The updated value of second grid point. Next, u2, sorry, u3f. U3f, in the sense, updated value of the grid point at 3. So with respect to this 2 and 4. u3, u4 of f. So this is what we are doing in the coding terminology. Okay, so here we have compared the different aspects. So different aspects of loops. So where here you can use for loop also. So the difference here is in the MATLAB what we have done. So we did not declare the data types. So CLC clear all, c is equal to 1, delta t is equal to 0.5, delta x is equal to 0.005, t is equal to 1 second. So this thing already, like in the MATLAB, the by default data type, it will take it as a float. Okay, so which has a 4 accuracy after decimal actually. Okay, so by default MATLAB will assign a float data type to any variable which we declare. Okay, so when we are solving this diffusion equation with the MATLAB, so what is happening, so when we define the value of time, or delta x, or delta t, or c value, or u value, or any value, it will be by default assigned with the float. Okay, so that is what we have, a simple level or a low level programming language which is from MATLAB. But when you are going in the object oriented programming language with say C++, or you can take Java, so what happens, like you need to declare the data types. So let's say, so here you will define what is C. Let's say it is a constant, you will keep it as a constant. Okay, or you can take int c is equal to 1 directly, and you can take in, or you will take here it is a float. So float delta t is equal to 0.005, float delta x is equal to 0.005. So you can take time t is int t is equal to 1 second, you can take that one, and remaining the values initially. So you have u1, u2, u3, u4, u5, u6 till u10. You will initialize those values. So the values of velocity you will keep it as float. So it's like so what happens, let's say u1, this is what we have. So how do we write and initialize is float u1 is equal to, let's say, 0.005. Okay, so next you can keep, so if the value is same initially for all the grid points, u1 comma, so you can declare it So u1 comma u2 comma u3, so on till u10 you can take. Okay, so this is what we can take actually. Fine. So that is the basic difference between the object-oriented programming language and the simple or the low-level programming language, which is MATLAB we have taken. So in this way, so we can solve the diffusion equation. So with the any numerical technique. So here we used Euler scheme. So simple forward difference. So simple forward in the sense. So let's you take dou u by dou t. So this is u2 minus u1 divided by delta t. So this is called the Euler derivative. So where this is a very simple and straightforward. So you have 2-point method, you have 4 or 6 method. So where the integration level will increase actually. So with which the accuracy will increase. Okay. So this have like high end programming nature, like more number of variables have to be declared, or you can in the MATLAB you can call the functions of ODE to solve these equations. So where it has its backend code to run and give the values of u1, u2, u3. So where direct ODE 45, ODE 18, these things are available in the MATLAB. But whereas in the object-oriented programming language, you have to define the methodology. Let's say you have to do this partial differential. So you will keep a function called PDE, and for that inside that function, like you will declare the class variables, you will use the constructor, and then you will keep the method. So what are the input variables that you need to be used for the calculation of this integration. So those functions you will declare in the function, those values you will declare in the function, and when you want to run the driver code, so like that inputs will be applicable in the driver code. Okay, so with the help of the driver code, that inputs are available, so that it will call that function, it will execute that integration method, and it will give the output. So this is what we do in object oriented programming language. So you can solve this diffusion equation in any way. So in the low level language or in the high level language, it's your interest. But if you see the low level language or the MATLAB, so the accuracy, let's say you will have the float, and so there by default you will give some, like it will assign its values. But here in the object oriented programming language, you can actually declare exactly. So let's say you have a velocity value of exact 0.00567, something like that. So if you need very precise value, so then you can go for it. And when you require a approximate value, you can go for this MATLAB with the simple declaration values. Okay, so with this actually we have seen our uh, solving technique of diffusion equation, whether you take 1D, 2D or 3D using any programming language. So what we have done, so we have taken a 1D diffusion equation. For the 1D diffusion equation, we have written the forward difference formulation for the explicit method. Once we get the explicit method, we have written in the form of MATLAB, and we have compared with the object-oriented programming language. So how to declare those values of u1, u2, u3, u4, u5, those values we will like we have seen. And then in the MATLAB, what is the main disadvantage? So by default, it will assign float for everything. Okay, so where if you know that value is a constant and integer, so even for that also you will apply float. Okay, so therefore, when you take this object-oriented programming language, you can assign your particular data types, so that you can solve your code or the diffusion equation accurately. With this, we had come to end of this power problematic case on the module 3. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.